Okay. You guys seem done. Are you guys done?
Yeah.
Yeah? You guys done with your group? Okay, perfect. Then, let's get started. So, keep whatever ideas that you had while solving this question in your head, because I'll be asking you to share as we go throughout class today. Okay, yeah, so let's just get right into it. So this is lecture 3, and we'll be talking about algorithms for SAT. As always, we'll do like some reminders and other housekeeping things. So homework 1, which is technically the second homework, is due on Monday, September 23rd at 11:59 p.m. This one is like going to be noticeably more time consuming than homework 0, because now we're actually like applying stuff that we learned. It's not just like Python warm up. Now it's a little bit more full force. So I encourage you to start early. It's not going to take like an extremely long time, but it'll take a good amount of time. So the sooner you start, the better. The other big change is that like starting now going forward, office hours we're going to hold online through OHQ. So you can just go to ohq.io, make sure you add the course 1921, and then, yeah, whenever we have office hours, you can just join through the queue. Just put a Zoom link. So Cindy's office hours are staying the same, Wednesday 6 to 7. I had to change mine. For now, it's going to be Saturday 6 to 7. Like my personal schedule is very crazy these coming weeks, so things may have to change. If we ever have to make a change to office hours times, we'll post it on Edge, just so that way everyone's aware. But those are the main changes. Actually, before we get to that, some people may have joined the class late, maybe like after homework 0 was due or right as it was due. If that is you and like you were not able to complete homework 0, please email me as soon as you can. Ideally, you would have already done that, but please email me as soon as possible so we can figure things out. But I think most, if not everyone here, has done it, so that's good. Just a brief reminder on grading. We talked about this in the first lecture, but not everyone was here. The breakdown looks something like this. Homework is worth 60%. It's not quite going to be evenly weighted. Homework 0 is worth a little bit less, something like 8%, and then homeworks 1 through 4 will be evenly weighted at around 13%. There's a final project, which will be 30% of the grade. We talked a little bit about it in the first 2 weeks, and as I've been saying, we'll get more into it midway through the semester, more information on that. And lastly, and most importantly, is attendance, which is 10%. And I made this point during the first lecture, and I want to repeat it for people who hadn't heard it. Attendance just isn't about like showing up. Like that is part of attendance. But the bigger picture here is being like actively engaged in class. That doesn't mean you have to answer every single question I ask or ask me a billion questions. I just want to see that you're paying attention, you're learning the material. At the end of the day, that's all I really care about. Did you guys learn the material? Grades are kind of like, you shouldn't worry about that. As long as you're doing the work and you're like actively engaged, you'll be fine in terms of grading. Do you have a question?
Yeah.
Yeah.
The homeworks, is it always going to be the case that like what we see is what we get for the auto grader in terms of the grades?
That's a good question. I'm going to avoid giving an objective answer and say that whatever you get will be extremely close to what your actual grade on the homework is. So if you get like a 93% through the auto grader, you shouldn't expect that your final grade to be like an 82. Like it might change to like a 92 or 94 just when we go in and do manual checks, but it's not going to be a drastic difference.
And are those manual checks typically just like denoted in the write-ups in case of any manual checking to make sure like we didn't like brute force when we were supposed to do something else type of thing?
Yeah, things like that, or whatever comes up. Good question. Any other questions? Okay. What else do I have? Yeah, okay, so just a bit of recap. Last week we talked about using SAT solvers in Python. So we talked about PycoSat, and we saw implementation of that in code. And then we also discussed how like SAT isn't the only problem. There's also graph coloring and stable matching that we can encode as SAT, and our SAT solvers can then solve those questions instead. But I think last week some people had the question like, how do these algorithms like actually work? Right now we're just putting in the input and it's giving us output, but like what's going on in the like under the hood? And that's sort of what we're going to look at today. So, okay, hopefully by now, we can recognize that SAT is a difficult problem, right? There's no way around that. And like, we say it's NP hard, it's like an exponential time problem, all of that. And like, really the question is, so then how can we solve it? Like, we must accept the fact that it is hard and it is exponential time, but how are we able to reduce that down to something more manageable? And by more manageable, we don't mean polynomial, because that would mean that it would be in P, just something that's more manageable in the exponential world. So, like, a first approach to solving SAT, I can test my whiteboard markers, is just like a naive search. You might call it like a tree search or DFS, but literally just try every single assignment of variables and wait until you get a satisfying assignment. And if you go through all of the assignments and it doesn't work, then too bad. Like, it's unsatisfying. So I'm just going to draw something here so we can refer to it later. This marker's bad. So the idea of like what this tree diagram represents is at the start, we have like no variables assigned. But as we like take a branch, we are assigning a new variable. So going down this first path here, we're setting, okay, x1 could be equal to true, or variable 1 is equal to false. That's the first decision that we make. And then we could decide for the second variable, whether or not it's true or false. And all of these intermediary nodes represent like, a subset of a decision we could make. Like we could theoretically want, variable 1 to be set to false and variable 2 to be true. And so in this representation, it's actually at the leaves where we have all of the decisions made. All of the variables have been assigned. So if that's the case, if this is where all of our decisions are, or all of our assignments are, and our naive search is just to try out all of these assignments, how many leaves do we have to try out? Like, how many leaves are there in this tree? Yeah, I mean, let's just say like there's n levels here, then we can just say like it's around 2 to the n leaves. So yeah, that's where we're seeing exponential. Like it's going to take a really long time to do that. Yeah, okay, so that's like the first approach of what we might do. But that's going to take too long. So what we'll do is simplify our search space. We'll use observations that we know about SAT to take our tree and say, hey, maybe some of these leaves I don't actually have to visit because I know for certain they're going to result in something bad. If we can do that, we're not necessarily making the problem polynomial from exponential. It's still exponential, but we'd be reducing the amount of work that we had to do. Like if I just said, these first 4 leaves are guaranteed to be wrong, we would just skip over those. And we're gradually reducing how much work we have to put into it. So that's the idea that we'll leverage here. Okay, so some people had this problem, and some people did not. So for those who did not, I asked them to find a minimal satisfying assignment for the following formula. And what that means is they should set as few variables as possible, such that however the other variables are assigned, the formula will always result in true. So who had this question? Your group and your group? Okay, you guys can go first. Tell me like what answer you came up with and how you went about solving it.
Well, we try to find the term that appears in the most number of clauses.
Mm-hmm.
That way we can satisfy all the clauses with just one variable. And we notice that not x2 appears in 4 out of the 5. So by setting x2 equal to false, we have 4 of the 5 clauses true.
Mm-hmm.
And then we just have to pick one of the remaining variables to satisfy the complete statement.
Awesome. So like what was the other one you chose?
x1 equals false.
X1 equals false?
Yeah.
Yeah, that totally works. Your group?
The same thing, I think, yeah. And then we were trying to discuss like what methodologies really work out here, because like one way to think about it is taking the literal as the most common. I think that's the first approach that we all thought about. But if there was one more clause out here that was just like x2, for example, that would break apart the entire algorithm because then x2 needs to be true. So we were trying to figure out like what's the best approach to do that.
Good. Yeah, hold on to that idea. So like the observation that both of your groups made is excellent, that like you notice that x2 or not x2 appeared in a lot of different clauses. So once we set that to true, we could more or less ignore those clauses. We didn't really have to worry about any other variables within that clause because we already set x2 in such a way that that variable would be equal to true. So this is a critical like first observation we can make. So here's just an example: x2 to false, x3 to true. Yeah, so that would be minimal. So yeah, like these are some critical observations that we can actually implement. And so the first thing is like for our formula to be evaluated to true, each of our individual clauses must be evaluated to true. Because in terms of structure, phi is just clauses that are put together with ands. And for a logical and to evaluate to true, all of its arguments must be true. So we need every single clause to be evaluated to true. But more importantly, this is kind of the observation that was made. Suppose we choose to set a variable equal to true, or maybe equal to false, then like the clauses that contain that positive x, that positive literal x, those clauses entirely get evaluated to true. So that is to say, like if we have a clause and one variable within it, we have set in such a way that it evaluates to true within that clause, then that clause is fully satisfied. No matter how the other variables are. They could be falses, they could also be trues. Since we have at least one thing being true, the entire clause is true. And the significance of this is that we can just remove that clause from consideration further, because we've already satisfied that clause with an assignment. Make sense thus far? Any questions? Let me get my water because I get parched easily. Okay, so then surely we can maybe answer this question. So read it and tell me what you think.
I guess each of the clauses containing that just gets a bit smaller, but they don't get fully evaluated in each session unless it's just the sole not x. And if you know it's just the sole not x, then you know that that assignment doesn't work.
Yeah, so I liked one thing you said at the start, that it gets smaller. Well, can you just talk a little bit more about what you mean by that?
Yeah, so originally let's say we have a clause with like 3 different literals, and one of those literals being x, then now the clause becomes just 2 literals.
Awesome. Excellent analysis. Yeah, like the idea is that if we set x equal to true, then not x will be evaluated to false. So within the clause, we can no longer just ignore the clause altogether. Before we were able to do it because it evaluated to true. Now we can't do that because we have a false. That doesn't help in contributing to like the evaluation of that clause, but all of the other variables within the clause still matter. So in this instance, we can ignore that literal, just that literal, not the entire clause. So yeah, that's the significance. If we set x equal to true, anytime we see a not x, we can remove that literal from our clause. Make sense? Cool. So this is something that we're going to call the splitting rule. And the idea is pretty simple. It's like essentially exactly what we came up with. Let me try writing this out just so we can refer to it. Where's the trash in here? Good enough. No one's going to touch that. So when we set, let's say, xi equal to true, then we can remove or ignore the all clauses containing xi. That's the first observation that we made. And like we can say a similar thing, that if xi was equal to false, if we set this to be equal to false, then we can remove or ignore all clauses containing what? Not xi. Yeah, it's just the same thing, but the inverse. And then the second observation we made is that when we set, let's say, xi equal to true, we can remove or ignore all literals that are not xi. That was the second observation. And then same thing, like if we were to set it equal to false, then we can remove all literals that are positive xi, because those get evaluated to false. So this is something, like I said, that we're calling the splitting rule, where we're just going to go through our formula. As we assign certain things, we'll remove clauses if they need to be removed, or remove literals if they need to be removed. And eventually, once we do a bunch of assignments, either we have removed all of the clauses, in which case all of those clauses had been satisfied, and then our formula is true, or we have a clause with nothing in it. We've removed all of the literals within the clause. If that's the case, then that clause has been evaluated to false. We've removed all of the literals, which means we've set all of them to false. So those will be like the two things that we check. If it's empty, then great. But if we have an empty clause, then not great. So let's do a quick example of this. So suppose my formula is something that looks like this. And let's just say, like, somewhere along I decide that the first thing I want to do is set x1 equal to true. This is like a decision I'm making. So using the splitting rule of removing things, what happens when we make this decision? Like, what does the new formula look like? Yeah.
x2 or x3 and x2.
Yeah, so
Not x2 or x3 and x2.
I need a different color marker. So yeah, like this first x1 gets evaluated to true, and so the splitting rule says we can ignore that clause altogether because it's been satisfied. The second clause has nothing related to x1, so that will come along. This is not x2 or x3. The third clause, this guy gets evaluated to false, so the splitting rule says we can ignore that literal, and so we can just say like and x2. And we'll call this formula phi given x1 equal to true. Just for a bit of notation. Okay, now let's say I made a different decision after this. And I said I want x2 equal to false. Here we would see that, okay, this now gets evaluated to true, so we can ignore this clause altogether. This gets evaluated to false, so splitting rule tells us we have to remove that literal. But critically, when we remove this literal, we'd be left with an empty clause. That clause has no more variables within it. We're not removing the clause, we've just removed all literals. So that would tell us that, okay, we have made a mistake. This is unsatisfiable under these decisions. And so what we would do is sort of like say, okay, this decision was bad, so let's try out a different decision. Maybe instead x2 equal to true. And then there, this clause would disappear, this literal would disappear, you'd be left with just x3, and you can set that to be equal to true. Good. Example makes sense for the most part? Yeah. Cool. Who has read the lecture notes before? You can be completely honest. If you haven't, that's all right.
Past lectures?
Past lectures, yeah.
Just the first one.
Just the first one? Okay. Not the slides, the lecture notes.
Yeah.
Were they helpful?
They were a little dense.
Dense?
Very dense, yeah.
Okay.
I prefer it over the slides.
Preferred over the slides. You guys preferred over the slides?
I was reading the one from last class, and I think that was helpful. I mean, I think it is dense, but like there are a lot of examples and stuff which make it really like concrete.
Okay,
Yeah, so
that's helpful. Yeah.
I didn't read through them completely, but I was just going over them. I feel like it's a very good resource in terms of like everything is out there. So if you ever want to find anything, like it's there.
Mhm. Yeah, I think like one thing I was thinking is that it is dense, which makes it annoying to read. But like if you need to come back to it and say like week 8 or week 9, it might help out then. But okay, I'll try to make it slightly less dense, but still helpful. Good. Okay, example made sense. Good, good, good. Just got to make sure I'm not taking too much time. So what's going on here, and like really what our naive search was, is something called backtracking. This is a general paradigm in a lot of different coding problems, including DFS. And the idea is like we continuously make decisions until we make a mistake. When we make a mistake, we say, that was a bad decision. So we retract that decision, go backwards, and make new decisions. And you can think of it as like searching in a maze. You know, you can search until you hit a dead end, but then you have to retreat and make a different decision. So that's the general idea that's going on here. It's called backtracking. Yeah, this is actually used in a lot of different problems, like graph search, like we said, even like permuting a set, like finding permutations of a set, or like the n queens problem. Lots of different applications of it. So this slide was just introducing the notation that we discussed, that like phi given x, or like phi given x1 equal to true, is just the formula we obtain after applying the splitting rule once that variable has its assignment. Okay. This is the pseudocode, which, let me think, do I need to write this down? Yes, I do need to write it down. So, like the algorithm that we have thus far, we'll call it backtrack, and it's given a formula phi. Maybe I need to use this phi. And like the first thing that we're doing is essentially checking the starting conditions. If it's empty, then it's vacuously true, or if it has an empty clause, which we represent with epsilon, that means it's unsatisfiable. And this, we shouldn't really think of this as like the initial state of the formula, because as you can see, this algorithm is a recursive process. So like after applying the splitting rule, we're checking these initial conditions on those formulas. So you can think of these as base cases. So first is like, if our formula is the empty set, then that's good, because that's exactly what it means to be satisfied. Otherwise, if we have this empty clause in our formula, then that's what it means to not be satisfied. Otherwise, we just go through the procedure. We choose a variable that has not yet been satisfied in our formula. And then we consider what happens when we set that variable to true and apply the splitting rule, or when we set the variable to false and apply the splitting rule. So here we would return backtrack of phi given x is equal to true, or backtrack of phi given x is equal to false. So exactly what we did in the example, just in terms of code. Kind of makes sense, more or less. Okay, if it doesn't, let us see a visual example of it. So, yeah, like we have this formula here. There are logical ands in between the clauses, but they're omitted for the sake of who knows what. And yeah, we'll just like run through this algorithm. So first we'll check like, is it the empty set? No, it's not. Are there any empty clauses? No, there aren't. So we would choose a variable, say in this case, variable 1. And we'll go down this left branch here, setting x equal to true, or in this case, 1 equal to true, and see what happens. So in the first two clauses, they become false, which, okay, fine. Nothing's really changed. Here we just ignore those literals, just applying the splitting rule. Then we can choose, then we're back up to here. We check the conditions, neither of which are true. So we'll choose a different variable, say in this case, number 2. And then we can go down this second path here. What happens when we set x2 equal to true? In this case, when the first clause, that second literal has now been evaluated to false. So we would remove it, which means we have an empty clause, a conflict, right? That means we made a wrong decision. We have to backtrack. So we'll try setting 2 to be equal to false. Now our first clause is satisfied. Hooray. Second clause, literal wasn't satisfied, so we'd remove it. Again, we don't have an empty clause, nor do we have all clauses satisfied, so we choose a different variable, say x3. Set that equal to true. Now the second clause gives us a conflict because we've removed the third literal, all literals have been removed, it's empty. That doesn't work. So we backtrack. Try 3 equal to false. Now the first two clauses are satisfied, third and fourth aren't. And we keep trying this. 4 equal to true works fine. 5 equal to true causes a conflict. So we backtrack, set it equal to false, and we have our, satisfying assignment. So all we're doing here is essentially performing DFS on this tree. Right? We're going down these paths, but sometimes we stop early because we've recognized, hey, we have an empty clause or something like that. That's good, right? We're not exploring all 2 to the n combinations. Things have been improved a little bit. But this raises a couple of questions. First, how do we actually compute this phi given x? How do we actually implement the splitting rule? But more importantly, we're still trying to make this algorithm something that's fast, right? So we want to be able to do everything that we discussed quickly. We want to be able to detect if we have an empty clause quickly. We want to be able to backtrack quickly. If we made a mistake, we want to be able to return to a prior state quickly. And we want to actually apply the splitting rule quickly. So these are all very important things. And we need to figure out how to do that. Okay, that's good. Okay, so let's answer the first question. The third question. How can we compute phi given x? And the answer could be extremely obvious. I guess.
I'm not sure if I'm understanding it, but
Yeah.
you could just linearly search the entire
Yeah.
just evaluate it for every time there's an x, and then if it's false, you just remove it. Otherwise, pass it.
Perfect. That's even a better answer than what I was looking for, which was just apply the splitting rule, right? But then you're going into how to actually apply the splitting rule, which is fantastic. The idea is we just do exactly what the splitting rule says. We delete the satisfied clauses and we remove the false literals from that from the formula. And if we're thinking about this from a data structure standpoint, maybe we implement things as a linked list. So I guess visually we can say our formula is this linked list. Haven't drawn one of these since CIS1921. And each of the elements is itself a linked list, which contains the literals within our clause. I don't know. Right, and
order, we can use sets as well, right? A hash set.
Maybe, yeah. But okay, let's say we go under this linked list implementation. Deletion is a very quick operation when it comes to a linked list, besides the part of figuring out what you want to delete. Because all it is just a rerouting of pointers, especially if we use a doubly linked list. We could have represented things as arrays, but then when you delete something, there's all of that shifting that occurs, which may add overhead. So, deletion works really well here. Are there any problems with a linked list implementation? Yeah.
Isn't accessing the elements very slow?
Accessing elements is slow. I agree with that. Do you guys think?
I mean, I guess like you're gonna have to do a search through every clause if you don't know exactly which clauses you're interested in. You would just like iterate through the whole linked list, which is O of n. I think in an ideal world, like if we have some sort of mapping from a literal to the clauses that contain that literal, then like we could optimize it faster.
Awesome. Yeah, like when we think about our algorithm and like the splitting rule, this step in particular, if we have an empty clause, in order to detect that, we would have to traverse through the entire linked list, which does take time. So, that is a potential issue. Another huge issue is like, how do we backtrack? Once we delete stuff from our linked list and we keep on making decisions and delete more and more stuff, and we realize, hey, we made a mistake, eventually we want to be able to get back to a prior state before we made those deletions. So like going back and inserting things to things we deleted, that seems like it's a lot of extra work. Is there a simple way to fix the issue of backtracking still under this like linked list implementation? Yeah.
This could be a crazy idea, but like something like a skip list where like if you want to delete something.
Too crazy. The issue is like, I'm going to edit this formula like as I make decisions. Maybe this formula is like located here on my decision tree, and I realize, hey, I made a mistake. I need to go back up here, but I've already deleted stuff.
Do we care about like memory usage? Because if we don't, then we can just store all the history of the prior states.
Yeah, exactly. If from here we pass down something called like phi, then maybe here we make a copy of phi. Like we create phi 1 and phi 2. Both of them are exactly the same. One of them we will edit. So like this will get passed down to its children, but we have a copy from before that we could ever reference if needed. But you brought up a really good point. So here we just make a copy of phi and then use that if we need it and then edit the other one. But the big issue is that it's very, very expensive. If we're dealing with like an exponential tree, which we are, and we're making a copy of phi at every single node, that is a lot of memory that we're using. It's a lot of overhead. So this doesn't quite work either. I just need some water. Okay. Turns out we can be very smart. We can go about not modifying the formula, nor copying it, which seems pretty crazy, right? Because like these were our solutions to it. But we can do something which allows us to, detect empty clauses a lot easier and things like that. And it's just, it's just a good observation. And the key observation is this. The only time we need to backtrack is when we have made a decision that is bad. Or in other words, we have made a decision that makes a clause false. Because that's our condition for saying our entire formula is false. That can only occur when our clause has just one literal in it. Because the decision we make would have removed that literal, yielding an empty clause. If we had two or more literals in a clause, that clause will not become empty after a single decision. Because at most we would just be removing one literal within it. So only clauses that have one literal in it are subject to become empty at the time of a decision. So that's going to be our key observation. And this gives us something called the one watched literal scheme. And it's exactly what we said. Like the observation is that a clause can only become empty if it has just one unassigned literal remaining. So the idea is like these are the only clauses we need to check. But again, it's like still kind of a problem. Like we would have to traverse through all of these and check if it's of size 1, blah, blah, blah. But this is the key idea here. Each clause is going to keep an eye on a single variable or a single literal within it. And that literal must satisfy some conditions. Either that literal has already been evaluated to true, in which case the entire clause is true and we don't have to worry about it, or it's unassigned, which means it's still subject to change. But if that literal is evaluated to false, that's no good, so we have to watch a different literal. And we'll see a visual example of it. But the idea is that each clause will watch a literal, one at a time. And okay, here's the example. So if something is colored in yellow, that is going to be the literal that the clause is watching. So for now, all of these clauses are watching the first literal in terms of like the sequence of things. And then we just proceed with our like normal thing. We'll choose a variable, set it to true or false, and see what happens. So, maybe we choose 1, set it equal to true. And now we'll take a look at the watched literals. In this case, only the first 2 clauses are watching the variable 1. And now they're both evaluated to false. Let me write it on the board just so we can reference this if needed. I don't think we need this anymore. Okay, so I just wrote on the board exactly what the one watched literal schema is. So it's if the watched literal becomes false, we'll watch a new one. Otherwise, if we run out of things, then the clause will be empty, and we'll see that in action. So yeah, back to this example on the board here. If we set 1 equal to true, the first 2 clauses, their watched literals, are now false, which by our schema tells us that we need to watch a new literal. So, we can do that. Just choose the next literal sequentially. We'll proceed through this algorithm. So we'd pick a different variable, say x2, maybe set that equal to true. Who wants to explain what's going on here? What do the colors mean, and what's the result of x2 being equal to true?
So because in the first clause, it was now watching the 2 literal, or not 2 literal, I should say, and then 2 became true. So it was like, crap, this is also false, but has no more literals to watch. So now it realizes it's empty.
Perfect. Yeah. So that first clause says we have a conflict. Its literal is now false. So the schema would say watch a new literal, but we can't because we've run out of literals to watch, which means it's empty. And sure enough, under x1 equals to true, x2 equal to true, if we follow the splitting rule, we would have removed both of those literals and it would be an empty thing. So perfect, exactly correct. This means we've made a wrong decision, we should backtrack. So we would try x2 or variable 2 equal to false. Yeah, okay, what's going on here and what should happen next? Awesome.
So for the second clause, it realizes that the second the literal 2 is now removed because it's false. So it'll in the next run it'll start watching the next literal in it, which is not 3.
Yep.
And the first clause it's satisfied, so it doesn't have to worry about it anymore.
Perfect. Yeah.
It'll be okay.
This only works because the literals are sorted, right?
Yeah, like, and because we're choosing the variables in that order.
Yeah, like in the sorted order.
Yeah. Do you think that's an issue though?
No, why do they need to be sorted?
No, it's not an issue because you can sort in polynomial time, so it's fine.
Exactly. Yeah, just
But
want to make
we-
sure
we
people
sort of-
recognize
if there's
this.
one or three, this thing or two in that.
I'm like.
Yeah, so like one thing that's kind of being swept under the rug here is that like these variables are sort of in order and we're processing them in order. If they were out of order, then maybe the way we watch things may not be sequentially. I mean, you can like try it out on your own and you'll see like
But the algorithm will just be like worse, right? It'll still work. Like,
it'll still work, but like in order, if we want to maintain this like cleanliness, it's pretty easy to just go through every clause and then sort them in order because sorting is a polynomial time operation. There's polynomial number of clauses, and if this algorithm is not polynomial in the grand scheme of things, it doesn't really
No, I
matter.
think I get what he's saying. Like the algorithm won't even work because, like, let's say we set 2 and like one of the clauses is not like 2. It needs to watch it like later in it if it's not sorted. Then it like won't realize that there's some mistake.
Yeah,
So it
exactly.
just, like, won't even work.
Okay, cool. So yeah, here, if we proceed on, like Madhav said, this second clause here, we have to watch a new literal. So we just shift the attention. The first clause is satisfied. So fantastic. And then we can go through it again. X3 equal to true. Third and fourth clauses are now satisfied. Second one is not. So the schema tells us we need to choose a new literal to watch. We can't. That means it's empty. That means we've made a bad decision. We have to backtrack. Conflict. So we try 3 equal to false. And, I won't bore you to death, but eventually, like, here we have to watch new literals for the third and fourth clauses. So we do that. Test out x4. And then test out variable 5. That doesn't work. Conflict. And do that. It's just following the rule. Take a mental screenshot of this tree right here. You ever do those like children book things where it's like spot the differences?
Yeah.
I was terrible at those. So whatever you memorized, spot the difference with this tree.
This is the same one or a different one?
This is a different, like this was from our backtracking when we did the backtracking algorithm. Spot the difference. What's the difference? No difference? Really? No. Why not?
Because you're essentially doing the same thing. It's just that in this case, technically by backtracking, you have to store all the previous information. In that case, also you were, in a sense, smartly backtracking because you were taking everything in order.
Yeah. Like, whatever we did with this one watched literal schema wasn't to, like, improve our search tree necessarily. It was to handle that issue of, like, finding the empty clause. Now it's just a matter of, like, all of these clauses have, are watching these literals. However you choose to implement that, I will intentionally be vague about it because you may have to do something like this on a homework. But now the point is, like, if a clause ever says, I don't have any literals to watch, then you know it's empty. So that's the purpose of this, just to, like, improve that one thing. But, maybe we still want to improve the search tree a little bit. Okay. And this is the other problem that a group had. So it must have been your group. So for them, for the other groups that didn't have this problem, this question was just a formula here. Give me a satisfying assignment. Just any satisfying assignment. So what did you come up with? What was your thought process?
So I think we just started with the smallest clause, which is just the literal x3 by itself. So we know x3's got to be true. Then we basically removed all of those literals and whatnot in the rest of clauses. We're left with a clause with not x1, so x1 has to be false. You repeat this process until you can kind of figure out everything.
Mm-hmm. I won't ask you to give me the satisfying assignment because that would take too long, but here is an example of one. But there are very, critical assignments here, which is, exactly what was mentioned. Like, there's this observation that the third clause is only x3. For that clause to be satisfied, we have to have x3 equal to true. If it's not true, no good. That is critical. But then also, if we look at the second clause, once we assign x3 to be equal to true, this one is now false. So this is just a single thing on its own. That must be true, which means we must have x1 equal to false. And then the rest is sort of like follows however you want to do it. But you can imagine that like these observations as a human, we saw that like, yes, we have that clause of one variable, let us set it to be equal to true. That is a great observation that we understand. But in our current implementation of things, we're still doing this like brute force kind of thing. And this observation ends up being super, super important to speeding things up. And it's called unit propagation. So for some vocabulary, a unit clause is a clause containing only one literal. So, does this work? Oh, yes, let's go. Okay, so this right here is a unit clause because it contains one literal. And the rule is like very obvious to us, I think. Like for any unit clause with like literal L, we must have L equal to true, which is exactly the observation was made. X3 must be equal to true. And it turns out that unit propagation can speed things up immensely. And, when I first thought about this, I was like, how? Because it's not guaranteed that every single formula that we get will look like this, where we have a unit clause at the start. So like, how does it speed things up? Yeah.
Sort of moving all the leaves one branch up, because like even though it doesn't have anything to begin with, once you start doing your, like what we were doing earlier with either the splitting method or like the one watch, however you say it, you end up reducing the clauses. So you always end up having clauses that are of size 1 before they go to 0. So
perfect. Yeah, when we use one watched in conjunction with the splitting rule, where we're going in and removing literals from clauses, like eventually some of these clauses are going to reduce down to one literal. And then that would be considered a unit clause. Yeah.
So in this case, is it like after the if it's sorted after the literal you're watching, if there is no other literal, then it's technically a unit, even though there's.
Yeah. For now, we'll think about it just in without like the one watched thing. We'll get to that in just a little bit. But like in terms of the splitting rule, once we detect that there's one thing left, we can just say, it's a unit clause. And so this is almost something called the DPLL algorithm. So this is, DPLL stands for Davis, Putnam, Lopeman, and Loveland. Some very, very famous names. 1962, which is over 60 years ago. But they basically took the observations that we made and implemented it. So this algorithm is literally just using backtracking, which we discussed, and adds on unit propagation. And it turns out to be really, really good, because that is pretty much the basis of a lot of modern day SAT solvers. Like 60 years later, we're still using these ideas. And the algorithm looks like this. And there's a reason why I wrote this on the board. Now let's play Find the Difference. And I guarantee there is a difference. Well, what's the difference now? Yeah.
You added in the unit clause.
Yeah, like the only thing is that we're just checking if there's a unit clause, right? And if so, then we like just go down that branch of setting that literal equal to true. We don't have to worry about this nonsense of setting it equal to true or false, because we know for certain there's only one correct decision we can make. So that's the same exact thing, just with like an extra check. And that's the great DPLL algorithm. Okay, good. Let's see. Good so far? How am I doing on time? Not terrible. Better than previous weeks. Okay, let's see an example of it. So, same procedure as always. This is a different formula, by the way. Spot the difference. So again, like choose a variable, maybe set it equal to true. Third and fourth clauses are satisfied. The first and second clauses, we remove that not x1 because that gets evaluated to false. So we recognize, hey, the first clause is a unit clause. Hooray. So we must satisfy that not 2, which can be done by setting 2 to be equal to false. But then clause 2 throws like a temper tantrum. That's a conflict. So now we have to backtrack. But where do we backtrack to? Like, what is the next decision we should make? Yeah.
we should backtrack all the way to 1.
Why not to 2?
Because like if a unit clause has failed, that means like no matter what we do with it, like it won't really work because that's a standalone thing. And, that's not working. So
Yeah, like the entire point of the unit clause was like, there's only one correct decision we can make. And if that failed, then we just don't need to consider the other decision. We'll go back up to the top. Right, so the next one would be setting 1 to false. So first 2 clauses are now satisfied, 3rd and 4th aren't.
this was not there in the pseudocode, right? Like in the pseudocode that we saw for DPLL, where have they exactly implemented that if the unit clause fails? Then you
So that's right here. So like before, if it's not a unit clause, we go exploring if we set it equal to true, or if we set it equal to false. If either one of those decisions ends in a satisfying assignment, then we're good. Here we're saying if we have a unit clause, then we will
just the
only
true.
consider the route where it's true.
makes sense. Thank you.
Good question. Yes, we did that. Set it to false. 3rd and 4th clauses not yet satisfied. So now we can try a different variable, 2. If we set that to true, clause 4 is satisfied. Clause 3 is now a unit clause, so we can just go ahead and say that must be true. And this is a much better search tree than like a full tree that has every single assignment, right? You know, it looks a lot better, and indeed it is a lot better.
Are there any quantifiers for like how much better something like this is? Because like in worst case, all of them are like just exponential.
Yeah, like in the worst case, it might not be making any improvements at all.
Yeah.
And that's like the whole thing about these hard problems, that like we are accepting the fact that it's bounded by 2 to the n, but for a lot of problems in this class, we may be making a lot of progress by using these
Do we ever
speedups.
know like how much, like for example, how much is DPLL better than like the naive backtracking by? Like, is there any way to like quantify that?
I mean, yeah, you could probably do some sort of like, you know, just go through all of the formulas of size, however much, and then compare the two. That's not something I know off the top of my head.
Like I
but-
remember in 121 we had these like few examples where like both of them are like linear time, but the constant is smaller for like one of them or whatever. So is there like something like this here as well? Right?
Yeah, not that I know of. Yeah, I think we would still say like it's bounded by 2 to the n.
Yeah.
Other questions? Okay. And like this is kind of what we were just discussing, that like we're not really evading the exponential part of all of this. We are still accepting defeat that this is an exponential time problem. But with that acceptance of defeat, we are saying any improvement we can make matters. Any speed up, because for a generic problem, those speed ups can really matter. So right now, like one of our drawbacks is this unit propagation step, like detecting a unit clause and then applying that. And so we can potentially speed that up. Another thing is that it's a recursive process, which recursive processes are long, they have a lot of overhead. It turns out we can make this an iterative approach. I don't really care too much about that, but maybe we'll cover it at the end. But the other part is important. Like right now, under the current description of DPLL, which, yeah, I'll go back up to here. How would you figure out if something has a unit clause? And you can imagine we're still doing like a linked list implementation. It should smell eerily similar to a previous question I asked about detecting an empty clause. What was the solution to that?
Not just a linear search.
Yeah, that was the first solution we came up with. Just check, do we have an empty clause, linear search. We can do the same thing, right? Just do a linear search, check if we have a unit clause. But then, what was the thing that we did to avoid the linear search? The schema that we came up with that would detect if we have a unit empty clause.
We came up with like the watcher thing, so it's like in a way like a pointer to the head of the particular like clause, so like the first element from that. So we can just like have those pointers, and for each clause we just see that if our pointer has a next pointer or not, and if it like doesn't, then it's a like single clause, and if it does, it's not.
Yeah, we used like the one watched literal schema, and that told us like once we run out of literals to watch, it's empty.
Yeah.
Here, we need it to tell us when there's one literal left. So, oh, darn, took away from the suspense. the 2-watch literal schema. And it's exactly what it sounds like. It's the same exact thing. Except now we're watching 2 literals. So now the key observation is that a clause can only be unsatisfied, or unit, if it has at most 1 non-false literal. Let me just move to the next slide. This is more important. The idea is we will watch 2 literals now. Same thing. If something is equal to false, let's watch a new literal instead. If something is true or unsatisfied, well, if it's true, hooray, we're done. If it's unsatisfied, we keep on watching it. And what happens here is, like in this example here, we're watching the first 2 literals, and suppose we set x1 equal to true. That makes this literal false, so we should watch a new literal. This second literal that we're watching, nothing changes, so we still keep an eye on that. But since this one is false, let's watch a new literal. And then if we make a different decision to set 2 equal to false, this one becomes false. We'd have to watch a new literal. We can't watch a new literal, but since we were watching 2 literals at a time, since we've now run out of new literals to watch, there's still one thing that we have our eye kept on, because we were watching 2 things, and one watch thing can't be done anymore. So we're left with 1. Very hard to explain it in words, but picture slightly helps, like a little bit more. It's the same thing as before, just 2 watch literals now. Yeah.
Do we know that like what we're doing here in like setting like 1 literal at a time is optimal, or like if we have like really big clauses, like could it make sense to like if you have 2 watchers as well, like just set 2 literals on one step and like do it that way?
So like instead of making a decision, set 1 to true, we say 1 to true and 2 to true?
Yeah, it's
Sure.
just like really big clauses, like maybe that could work.
It might work. It's just engineering matters. So, yeah, there's a bunch of different speed ups you can do. Oh gosh, okay. I guess I have to talk about this now. Okay, so the other thing is that DPLL, as we wrote it, was a recursive process, which in general is a long process and it has a lot of overhead in terms of like space and things like that. So we can actually make it iterative. And I don't want to bore you or myself with this information. You can look at it if you want. But the idea is like, let's just maintain a stack. And our stack will be of these arrays that contain intermediary decisions. So you can imagine like we're at some node here and like whatever variables we have decided on, those are going to be represented in our array on the stack. So, first we might set 1 equal to true. So we put that on the stack. And then later we may put 2 equal to true. And as a result, we propagate 3 equal to false and put that on the stack. And then do something else. Then the issue is like, what happens when we have to backtrack? The idea is just pop whatever was on the top of the stack off. Because now we go back to the state that we had before we made such decisions. Right? Before we set 4 and 5. Yeah.
Wait, could you explain the propagate 3 as false?
Yeah, this is just like hypothetically if this was something we did in like a formula, like if these were the decisions that we made. Okay. It's not like a specific example. It's just like, let's say we set 2 to true and then we had a unit clause where 3 had to be set to false. Yeah. So like when we backtrack, we can just pop something off the top and then we get the state that we had before it. And that makes it an iterative approach. And here's the pseudocode. We can try to talk through this, but I don't really like this too much. But it's like whatever we had, just in words, now in code. So like the condition is while all variables have not been set, because we need to set all variables have our satisfying assignment. Then we do the same thing, choose a variable. Then we create our new decision level. Then we can set that variable equal to true, so like that is a decision we can make. And then check if unit propagation can occur. Like if we have a unit clause, then great, we'll do unit propagation. If that causes a conflict, and the decision level is 0, meaning we're like back to the start, then we can just say it's unsatisfiable. Otherwise we backtrack, and again, I'm leaving this somewhat vague because I want you to think about this a little bit more. And then once we backtrack to the start, before we made like x equal to true and before we did all of this propagation, now we'll consider what happens if we set that variable equal to false. And then, check the unit propagation again.
The decision level is basically your stack level, right?
Yeah, it's like, you can think of like the decisions you make as a tree, like my first decision is setting this equal to true or blah, blah, blah. And yeah, so think of it as a stack. And then one last thing that might be helpful to think about is how do we branch? And we've brought up questions about this throughout the lecture today, which is like, we've sort of just been doing things in order and like picking the variable. It's just like, whatever's next, we'll set that equal to true. However, like the order in which we assign variables can affect the runtime. And like as an example, if we had this formula right here and we went about like setting 1 its value and then 2 its value and so on and so forth, that's fine. That would be okay. But it turns out it would be a lot quicker if we just set variable 6 first, followed by variable 7. Because no matter how you assign 6 and 7 in this example, one of these things will be equal to false. So if at the start we just said, let's set 6, then great. As humans, we can see this with our eyes, that I'm going to choose 6 first. But like when it comes to coding it, like we need a general solution that can still potentially detect these things. So, and so like there isn't a great answer to this of like how it's solved. It's not just like, let's implement this technique right here. Instead, we use heuristics and like sort of observations we make along the way. So there's static heuristics and dynamic heuristics. So we've sort of just been doing static heuristics where we choose a variable, like we have this fixed ordering, we went 1, 2, 3, 4, 5, and we made those decisions. That's fine. We may choose to use dynamic heuristics where we change the way we choose variables on the fly. And that's fine. It's actually more effective. But it ends up being more expensive. If we have to do these computations at each decision level and rearrange the variables, again, we're still working with an exponential search space. So the more work that we do at each node, it's going to add up a lot more. It adds a lot of overhead. But still, these heuristics can be done. So, you could just use a random ordering. That can work better. You might do this thing called most frequent static ordering. I don't really know what that is, so maybe you could do that. Or most frequent dynamic ordering. The point here is that these worries, these qualms that we had about like the current implementation, the current approach, people have thought about that. There's just no great solution because we're still looking for a general solver, something that can solve all of these SAT problems. We may make changes that are specific to one formula, but in turn, it could make it worse for a different formula. So things stay very general here. So that's it for today's lecture. That's pretty much all I wanted to talk about today. Just exploring like the different algorithms that we use. And like the key thing that you should take home here is that we're not making SAT a polynomial problem. We are still saying it is an exponential time problem. However, we need to speed it up however we can. And with 1 watched, with unit propagation, with 2 watched, here we're seeing we can make decisions a lot better on the fly when certain things come about. Cool. That's about it. As a reminder, homework 1 is due on the 23rd, whenever that is, like a week and a half. Start early on it. If you have questions, post on Ed. Hopefully everyone's on Ed. If not, I'll sync it again tonight. And yeah, that's about it. See you guys next week.